This video is a brief description of how the periodic table follows naturally from quantum mechanics. So in 1869, the Russian chemist Mendeleev postulated the periodic law, which states that when the elements are arranged in order of their atomic number, then elements with similar chemical and physical properties will recur at regular intervals. So in the periodic table, the elements are arranged according to their atomic number. So the number here is the atomic number in a series of rows. So each row here is known as a period, okay? And elements with similar properties form vertical columns. So each column is known as a group, okay? So these are the number of the period number, and this is the group number. So for example, group 1, it consists of hydrogen and also the alkali metals. And the alkali metals have low melting points and are soft and are very active chemically, okay? Such as, for example, lithium, sodium, and potassium. So note here how hydrogen is in the same group with the alkali metals, although it is not a metal, but it behaves chemically like an active metal, okay? And for example, the group here consists of halogens, which are nonmetals, such as fluorine, chlorine, bromine, and iodine. And this group, for example, it consists of inert gases such as helium, neon, and argon. And they are named inert because they are inactive chemically, okay? So the first three periods here are broken to keep their elements aligned with closely related elements in the period below, okay? So as you can see from this figure, the majority of elements are metals, okay? And along each period, there is a transition from an active metal to less active metal, and then to weakly active nonmetal, and then to highly active nonmetal, and then finally to an inert gas, okay? And also along each column, there are also regular changes in the properties, but it is less pronounced than across each period. So this figure here shows how the chemical activity varies in the periodic table. So you can see, for example, that increasing the atomic number in alkali metals is associated with more chemical activity, okay? And the opposite is true for halogens. So quantum theory was able to explain the periodic law without any new assumptions. So the periodic law arises naturally in quantum physics. So for atoms with more than one electron, there are two principles that determines its structure. The first is the fact that a system of particles is most stable when its total energy is minimum, okay? And the second is, as mentioned in the previous video, about the Pauli's exclusion principle. So according to this principle, only one electron can exist in a certain quantum state. So to show how the electrons occupy the various subshells in an atom, let us first consider how the electron's energy varies with the quantum state it occupies, okay? So although electrons in an atom interact with each other, it is still possible to understand much about the atomic structure if each electron is considered to exist in a constant average effective electric field. So for a certain electron, this effective field is approximately that produced by the protons in the nucleus, which is Ze, and decreased due to the partial shielding of the other electrons that are close to the nucleus, okay? So electrons that have the same quantum number n usually, although not always, but they usually are at roughly the same average distance from the nucleus. And this means that electrons with the same principal quantum number n are roughly in the same effective electric field, and so they have similar energies. So it is said that electrons with the same principal quantum number n occupy the same atomic shell, which are denoted by capital letters, okay, according to the scheme. So 1 is the atomic shell K, and 2 is L, and so on. And in addition to the energy of the electron depending on n, it also depends to some extent on its orbital quantum number L. Although not as much as it depends on the principal quantum number n, okay? So the amount to which the full nuclear charge is shielded from a certain electron by intervening shells of other electrons varies with its probability density distribution. So an electron with a small orbital quantum number L is more likely to be close to the nucleus, okay? And so it would be less shielded by other electrons than an electron with a higher orbital quantum number L. If both electrons were in the same atomic shell n of a certain value, so this means that the electron with the lower L has a lower total energy, which means a higher binding energy for that electron. So for example, for n equal 2, an s electron would be closer to the nucleus and so less likely to be shielded, and as a result would have a higher binding energy than a p electron in the same atomic shell. So in the same way that electrons with the same principal quantum number n occupy the same atomic shell, also electrons that have the same orbital quantum number L that are in the same atomic shell occupy the same subshell, okay? So electrons in the same subshell would have the same values for n and L, okay? And all electrons in that subshell would have almost identical energies, because the dependence of the electron's energy on the remaining two quantum numbers, ml and ms, is comparatively minor, okay? So now let's see how the electrons in an atom occupy the various subshells following these two principles, okay? So the notation used is that each subshell is identified by its principal quantum number n here, followed by the letter that corresponds to the orbital quantum number L. So n shows the shell, and the letter which corresponds to L shows the subshell, okay? And the superscript here after the letter indicates the number of electrons existing in that subshell. So let's take as an example sodium. So this shows the electron configuration for sodium, okay? So in the 1s subshell, which corresponds to n equal 1 and L equals 0, there are 2 electrons. And in the 2s subshell, which corresponds to n equal 2 and L equals 0, there are 2 electrons here, okay? And in the 2p subshell, which corresponds to n equal 2 and L equal 1, there are 6 electrons, okay? And in the 3s subshell, so it corresponds to n equal 3 and L equals 0, there is only 1 electron. And note here that the exclusion principle limits the number of electrons that can occupy a certain subshell, okay? So for a certain principal quantum number n, L can have these values, okay? So there are 2L plus 1 different values for ml, because ml can have these values for a certain L. And for each value ml, the spin magnetic number ms has 2 possible values of plus or minus half, okay? And so each subshell can contain a maximum number of electrons of 2 times 2L plus 1. and the maximum number of electrons a shell can hold is the sum of the electrons in its filled subshells, okay? So for a certain shell of a certain principal quantum number n, the maximum number of electrons it can hold is n maximum is equal to sigma from L equals 0 to L equal n minus 1 of 2 times 2L plus 1. So the sum here is over the number of subshells, and this is the number of electrons in each subshell, okay? And the quantity in the brackets here, it has n terms and it has an average value of half times 1 plus 2n minus 1, okay? And so the number of electrons in a filled shell is equal to 2n squared. So for example, for a K shell, if there is a closed K shell, so it is full to its maximum capacity, then it would contain 2 electrons because n is equal to 1. And the closed L shell, it contains 8 electrons, and the closed M shell, it contains 18 electrons, and so on. So let's consider some examples of the electronic configuration in some of the lighter atoms. So let's first consider hydrogen. So in its ground state, it can be described by either of the two sets of quantum numbers, okay? And the electronic configuration is written as 1s1. So only one electron is present in the s subshell. So let's consider neutral helium, which has 2 electrons, and in its ground state, the quantum numbers of these 2 electrons are given by these two sets, okay? So the K shell here is filled, and we write the electronic configuration as 1s2. And for neutral lithium, it has this electronic configuration, so it has 3 electrons, and in its ground state, 2 of these electrons are in the 1s subshell, and the third electron is in the 2s subshell. And the figure here shows the electronic configuration of some other elements. So for example, here the 2p subshell in boron has only 1 electron, okay? So 2p1. And this electron can be described by 6 sets of quantum numbers corresponding to 6 states of equal energy, okay? And also notice here how carbon has 6 electrons, and notice how the 2 electrons in the 2p subshell, how they are arranged. So instead of going into the same orbital with paired spins up and down, they occupy different orbitals with unpaired spins, so both are pointing up. And going back to the principle of least energy, where a system of particles is most stable when its total energy is minimum, it was experimentally showed that the configuration that is most stable and energetically preferred is the one in which the 2 electrons occupy different orbitals with unpaired spins. And also note here how the 3 2p electrons in nitrogen have unpaired spins, okay? So the general rule for this situation is known as Hund's rule. So Hund's rule states that when an atom has orbitals of equal energy, then the order in which they are filled by electrons is such that a maximum number of electrons have unpaired spins. And there are some exceptions to this rule in elements that have sublevels close to being filled or half-filled. And Hund's rule is due to the fact of the mutual electric repulsion of the electrons in an atom, okay? And because of this repulsion, the farther apart the electrons in an atom are, the lower the energy of the atom, okay? So consider here these two electrons which are in the same subshell. So they have the same L value, okay? So they are in the same subshell. If these electrons have the same spin, which means they have the same ms value, then they must have different ml values according to Pauli exclusion principle. And because they have different ml values, so here there are three ml values, which is 1, 0, and -1 for the subshell P, which corresponds to L equal 1. Okay. So because they have different ml values, they are described by wave functions whose spatial distributions are different. Okay. So it means that these unpaired electrons occupy different orbitals, which minimize the electric repulsion between them, and so it lowers the energy of the atom as a whole, and that is why it is the preferred configuration. Okay, so electrons with parallel spins are more separated in space than if they are paired off. So this arrangement of parallel spins has less energy and is more stable. So one consequence of Hund's rule is the ferromagnetism of iron, cobalt, and nickel, okay? Because the 3D subshells in these atoms are only partially occupied. And according to Hund's rule, the electrons in these subshells do not pair off, and so that their spin magnetic moments do not cancel out. For example, in iron, 5 of the 6 3D electrons have parallel spins, okay? So each iron atom has a large net magnetic moment. Also, note regarding shells and subshells that an atomic shell or subshell that contains the maximum number of electrons is said to be closed, okay, like this one. So a closed S shell, which corresponds to L equals 0, has 2 electrons, okay? And a closed P shell, which corresponds to L equal 1, has 6 electrons, and a closed D shell that corresponds to L equal 2 has 10 electrons, and so on. And the total orbital and spin angular momenta of the electrons in a closed subshell are 0, okay? And their effective charge distributions are perfectly symmetrical. Note also that regarding Hund's rule, some exceptions to Hund's rule can occur in elements that have sublevels close to being filled or half-filled. Also, electrons in a closed shell are very tightly bound, like this case here, because the positive charge is large relative to the negative charge of the inner shielding electrons. Also, an atom with only closed shells has no dipole moment, and so it does not attract other electrons, and its electrons cannot easily be detached. So atoms with a closed shell configuration are expected to be passive chemically, and this is the case, for example, in inert gases, which all have closed shell electron configuration or their equivalents. So as an example of electron shielding, let's take the example of sodium and argon atoms, okay? So as you can see, for argon, each outer electron here is acted upon by an effective nuclear charge 8 times greater than that acting on an outer electron in a sodium atom. So because the effective nuclear charge for an outer electron in argon is plus 8e, so the electrons are more tightly bound, and so argon atom is smaller in size and has a higher ionization energy because the outer electrons cannot easily be detached. Also note that in actual atoms, the probability density distributions of the various electrons overlap in complex ways, okay? So this changes the amount of shielding, but the basic effect is still the same. So an atom of any alkali metal of group 1, such as sodium, has a single s electron in its outer shell, and such an electron is relatively far from the nucleus. Also, it is shielded by the inner electrons, okay? And the effective nuclear charge is approximately plus E instead of plus Ze. So the outer single electron can easily detach from the atom, and this is why alkali metals here, they can form positive ions of charge plus E easily. So this is why alkali metals have low ionization energy, unlike inert gases, okay? Also, the larger the atom, the farther the outer electron is from the nucleus, and the weaker is the force that holds it to the atom. And so this is why the ionization energy decreases as we go down along a group. And also there is an increase in the ionization energy from left to right across any period, okay? And it is due to the increase in nuclear charge, while the number of inner shielding electrons stays the same. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.